Welcome back. So in this lesson we will implement PCA from scratch again, but for data preprocessing. So we will see how we can use PCA for data preprocessing for classification and regression tasks, and you can do the clustering on your own, right? So we will have a function, right? And we will call this function PCA, and let's call it PCA from scratch, or let's call it my PCA. Right, so let's call it my PCA. And this function, it will just do 3 steps. It will take the mean of the data, right, center the data, which is very important, and we will typecast it into an integer to avoid any typecast errors, and then we will subtract the mean, okay, and then we will perform the singular value decomposition, our function we implemented before. So this function will just return u, s, and v. So this is pretty simple. Okay, now we want to talk about something called the intrinsic dimensionality. So if we have a data set that contains n samples and d features, so how many features we have? D features. And how many samples we have? N samples. And if the number of dimensions we have, or the number of features we have, is much less than the number of samples or examples, so we have, let's say, 1 million examples and 100 features, right? So the number of features is much less than the number of examples. Then in this case, we may have many of the features containing redundant information. So they are not really adding anything. Let me give you an example. Let's say we have a feature for the length, right? The length in meters. And then we have another function for the length in centimeters. So these two features are completely dependent on each other, right? If we remove one of them, the other one will not be affected, right? Or the full algorithm or the full data will not be affected. So the concept of the intrinsic dimensionality, or when we say intrinsic dimensionality, we mean the number of dimensions we need to reconstruct the data with high fidelity, right? So the intrinsic dimensionality is how many dimensions we need to reconstruct the data with high fidelity, right? So we will define it as a number or as a percentage, and we will see how. And it can correspond to the number of principal components needed to reconstruct 98% of the data variance, for example. So basically what will happen is that we will give the algorithm how much variance we want to preserve. So let's say we want to preserve 98% of the variance, and the algorithm should return how many components we need to have. Okay, so it will return how many components we need to have in order to reconstruct 80%. So instead of just trying different components, we will just have how much variance we want. So we will stop at, let's say, something between 5 components and 10 components, right? Because this one is returning 97 or 95, something between this, and this is returning 98, 97, right? So something between 80, between 5 components and 10 components, right? So this should be the output from this code, right? It's basically the intrinsic dimensionality. And we define a set of features as linearly independent in the z-space. The z-space is our new space, right, that we are going to project the data on, if we cannot construct one out of a linear combinations of the others in the z-space. Right, so basically the number of linearly independent features in the z-space is equal to the number of the non-zero eigenvalues. So if we have a 0 eigenvalue, if we have a column that contains 0 eigenvalue, then this means this column is completely dependent on the other columns. Or let's say it in other words, if we have an eigenvalue that equals 0, then the eigenvalue is corresponding for a specific column. Then this means that this specific column is actually a linear combination of the other columns, right? So we can just remove it. Okay, so the number of linearly independent features is equal to the number of non-zero eigenvalues. And here we will define our 0 as anything less than 10 power negative 9 due to floating point error, right? So anything less than this number will be assigned as 0 or defined as 0. So 0 eigenvalues mean that the corresponding features are dependent on other features according to the matrix rank definition. So this is also another linear algebra concept. Okay, so let's see how we can implement the intrinsic dimension. So we will give it S, right, and we will give it the recovered variance we want to have. So by default, let's say 0.98. So this should return the number of dimensions. So if you remember how we calculated the variance, right, we get S, right, square it and then divide by the number of dimensions. So this is the same as in part 1, and we get the significance and we sort the significance, right, in descending order. And then let's say that the total variance at the very beginning is 0. The number of dimensions is also 0. And we have the recovered variance equal 0.98. So we will have a while loop, right? So while the total variance is less than or equal the recovered variance, then we are getting the significance of the current dimension and add it to the total variance, right? So the first time we'll have the total variance equal to the variance of the first dimension, or the significance of the first dimension. Then we will add 1 to the dimensions, right? And we will call it the second iteration, and we will get the significance of the second dimension, add it to the total variance, and do this step until the total variance is bigger than the recovered variance. Then we are going to return the number of dimensions, right? This I is not important at all, so we can remove it from here, right? So we have the number of dimensions at the very beginning is 0, and then we are returning the number of dimensions after we iterate in this while loop. So this should return the number of dimensions we need. Okay, then we want to know the number of linearly independent features. So we said that the number of linearly independent features are basically the features that their eigenvalues are less than 10 power negative 11 or 10 power negative 9 or whatever. So I define it here as 10 power negative 11, right? So we will get the eigenvalues again, and after getting the eigenvalues, I am returning the length of this list. So what is this list? It's basically if I is bigger than or equal epsilon, I for I in eigenvalues. So let's write it in another way. We will write I for I, right, in eigenvalue. How we write it? So we write for I in eigenvalues. What we are going to do, let's create some empty list here, right? And we will have an if condition. So we will write if I is bigger than epsilon. Then what we are going to do is that we will append, right, I. So this is, after that we will write that dimensions is equal to the length of M. So you see 1, 2, 3, 4, 5, these 5 lines are basically this line, right? So we are going to iterate over the values in the eigenvalues, right? So the current I is the current eigenvalue, and we will have in this list the values that satisfy this condition if I is bigger than or equal epsilon, right? And we will append this to this list, a list on the fly, right? We are creating this list on the fly, and we are getting the length of this list. So this list will contain the values that satisfy this if condition, right? So it can be the number of dimensions or less. So the number of dimensions we have in the original dataset or less than that. And it will be less than the number of dimensions if we have one of the eigenvalues less than 10 power negative 11 or 10 power negative 9 or basically 0, right? So this is basically how this function will work, and it will return the number of dimensions, the linearly independent dimension. And this dimension is different from this dimension, right? This is the dimensions we need to rebuild at least the recovered variance, right? And this is the number of linearly independent features. Okay, so this is basically how we can define our PCA. Now we will apply the PCA on data for regression. So we will load the Boston dataset. This is a dataset also from sklearn, right? And this dataset contains house prices. So here we have X and Y. We have 13 features in X and 1 value for Y, or 1 column for Y. This Y will contain the prices, right? So this is a regression task. Now, how we can apply the PCA on the data? We have another function for this, right? So we will come here and write my PCA, right? We will call first my PCA. So this will return U, S, and V after the pre-processing, get the intrinsic dimensions, get the number of linearly independent features, and what we are going to return is basically U times S, right? So we are going to multiply U by S. We don't want V anymore. We are using this V if we want to reconstruct X, but here we are not reconstructing X. We are just projecting X, or getting the reduced dataset. So what is a reduced dataset? U till the intrinsic dimensions, right? How many dimensions we need, or basically K, right? But we are not using K anymore. Okay, we are getting the number of dimensions, or the K itself, using the intrinsic dimension function, right? And we are multiplying this by S in order to return X with the same dimension we had before, and that's it, right? So what we are going to do here, apply PCA on data, the X data. This should return X PCA, independent features, intrinsic features. So if we run this, you will see that we have how many dimensions? We have 3 dimensions. So the same number of examples, right? 506, and only 3 features. So this means using only 3 features, we can recover the data with 98% information, right? Or variance. So this is like a huge finding. And how many features are independent? All of them are independent, right? Not a single one of them is actually a complete linear combination of the others. Okay, and how many intrinsic dimensions we have? We have 3 intrinsic dimensions. Okay, so this is really good. So we are going to use a train test split function, okay, which will return x train, x test, y train, and y test. And after doing so, we are going to use the SVR, support vector regressor, right, in order to get the predicted label. So we are going to create this classifier, fed the data, predict the data, and then we compute the mean squared error. So if we compute the mean squared error with the PCA, right, why with the PCA? Because the data that we are using right now is the XPCA, the data after projecting, right, the data using only 3 components. And the mean square error is 51.2, right? Remember this number. Now we are going to do the same exact thing, but without PCA. So we are going to train test split on the X, right, on the original dataset with the 13 features. And we are going to use the same support vector regressor for getting the predicted labels. So I'm going to do the same. And then we are going to compute the mean square error, right? This is the mean square error, not the root mean square error. And as you can see, the mean square error with the PCA is 51.2, and the mean square error without the PCA is 49.3. So there is a very small difference in terms of the error with using the PCA and without using the PCA. Although here we are using 13 features, and here we are only using 3 features, right? So this is how the PCA can be used for dimensionality reduction. So it's a very important application, and it can be even more interesting if we have 100 features or more. And you will see that in terms of the time, it takes so little time in order to run, while on the other hand, if we are using the full dataset, it can take a while to run, right? So this is basically how we can use, or how we can implement the PCA for data pre-processing for regression tasks, right? So this is a very interesting finding. Now in the next lesson, we will use PCA for data visualization. So we are going to implement our visualization function, right? And we are going to use PCA for visualization for the iris dataset and the wine dataset. These are 2 datasets that you can find in sklearn. We saw one before, and the other one we are going to discuss. So let's go to the next lesson and see all this.